This is the fourth video on multivariate twin modeling. And in the last video, I talked about the independent pathway model. And in this video, I will continue talking about it. What I'm going to talk about is, well, first, I'm going to do a short recap of the independent pathway model. So what I talked about last time. Then I will talk about fitting the model and comparing the fit of different models. Then I will talk a bit about interpreting and reporting results of the models we have fitted. Again, just a short slide on notation for you to go back to once you get confused, maybe later on. So as a recap, last time I introduced the independent pathway model in the previous video. And basically it was the common factor model applied to our additive, non-additive, and non-shared environmental covariance matrices. So here on the top left is the model in matrix algebra, right? We want to represent our sigma A, sigma D, sigma E in terms of the independent or in the common pathway, common factor model, sorry. So I've shown it here in matrix algebra on the top left, but also in the figure below, actually two figures, one for each twin. So here in the first part of the equation, before the plus sign, this gives you the common effect. So the common A, D, and E effects common to all four phenotypes. The part behind the plus sign gives you the phenotype specific, unique, additive, non-additive, and non-shared environmental effects. So, and to make it a twin model, to be able to estimate it, we need to connect the genetic effects across twins, right? Like we've seen here, like we see here before, like we've seen before, and like we see here in the expected covariance matrices of MC twins on the left and DC twins on the right. Well, this connection is pretty straightforward by now. I've also shown it in the last video. Additive genetic effects correlate 0.5 across DC twins and 0.25 for dominance genetic effects. So we do this for the common genetic effects and the unique genetic effects. So now this is the independent pathway model, and we can actually estimate this. So let's do this and compare different models using the likelihood ratio test. I think you've also seen this before, these likelihood ratio tests. So this comes back again here. First, let's start with the sigma D, so our non-additive or dominance genetic effects. So on the top left, we see the genetic dominance correlations, as I've shown you also in the previous video. Well, these are very high, all close to 1, and some of them even a bit larger than 1. And in the last video, previous video, I also talked about how this can happen, namely because we simply estimate or ask the software to estimate unconstrained covariance matrices. So we do not impose any constraint on these values. They can take any value. So sometimes because of sampling variability, these can turn out a bit larger than 1, which usually indicates that they are actually 1 or close to it. So if we see these high correlations, then it makes sense to fit a common factor model to this, to our sigma D. Why? Well, if the correlations are so high, then this implies that there, or it indicates that there may be some common dominance genetic, that there may be a common dominant genetic cause underlying the phenotypes, right? High correlations, genetic correlations imply that the genetic factors influencing on phenotypes highly overlap, so that they're basically maybe just overlap so much they're just the same dominance genetic factor, right? So the correlations tell us something about overlap or similarity. If they're so similar, then probably they're just all indicators of one and the same thing, right? So to take you through it, well, the dominant genetic effect on biceps is almost the same as the dominant genetic effect on triceps. The dominant genetic effect on triceps is basically the same as the dominant genetic effect on the S phenotype. So basically, it all seems like they're all due to the same factor. Well, a next logical step then would be to test, if we see these correlations, whether the unique non-additive genetic effects are actually zero. Why? Well, again, this follows from the high correlations, which are practically 1. Let's think about the residuals, what they do. These unique genetic effects literally make the phenotypes more unique. If there's no uniqueness, if the residual variance is equal to 0, then these phenotypes are actually exactly the same, right? If they correlate perfectly with each other, they are basically the same, which means that they are all perfect indicators of the common factor. They are all only causally dependent on the common factor. So they will correlate perfectly. Think about the bread baking example I gave earlier, right? We have a chunk of dough. We make 4 little chunks of dough from the same source. If we bake 4 loaves of bread and the conditions are the same, each time we bake a loaf of bread, if they're perfectly the same, then each loaf of bread will taste exactly the same, right? Because there's no unique element to each of the loaves of bread. So the correlation between the taste of the loaves of bread is basically 1, because they will all taste exactly the same. Well, the same holds for this correlation matrix. So first, as I said, what we want to test is we want to answer the question, well, is there a common dominance genetic factor influencing all of the 4 phenotypes? And we can actually test this. We can test this by first fitting the unconstrained multivariate ADE model and then applying the common factor model to our sigma D as shown in this circle here. And remember, in the previous video I said that in the unconstrained ADE model for each variance component matrix, we then have 10 elements we estimate. If we apply the common factor model, in this case on the dominant genetic effect, then we only estimate 8 parameters, right? So 10 minus 8 is 2, a difference in 2 parameters between these models. So then we can actually use a likelihood ratio test to test whether this common factor model applied to our sigma D is a better depiction of our data. We can use a likelihood ratio test for this, where we take the difference in the -2 times the log likelihood values of the models. We have 2 degrees of freedom, as I explained before. And then we compare this test statistics, which is 0.73, to a chi-square distribution with 2 degrees of freedom, and we see that the p-value is 0.69, which means that our constrained common factor model applied to D does not fit significantly worse than the unconstrained ADE model 4.1. So in that sense, the model seems to hold. Well, we do the same for, what we do then is, as I explained in the previous slide, we test whether the unique dominance genetic effects on the phenotypes are equal to 0. Then we have a test with 4 degrees of freedom. Why 4? Well, first we estimated 4 unique variances, and now we do not estimate them, we simply fix them to 0. So this difference between model 4.3 and 4.2 is the degrees of freedom of 4. We see if we test the difference in -2 log likelihood values between these 2 models, that again, the model 4.3 seems to fit well. So we would accept this model. So this is in line with no unique dominance genetic effects on phenotypes, effectively setting the genetic dominance correlations to 1, right? So what we can do next is then also continue with this model, apply the common factor model to the non-shared environmental effects, to sigma E. And if we do this, again with 2 degrees of freedom difference with the previous model, see that the test statistics is highly significant. However, if we compare the expected or model implied E covariance matrix between model 1, so our fully unconstrained model, with model 4.4, in which we impose the common factor model to sigma E, then we see actually that these values are roughly similar. So normally, if you would do this test, you would maybe reject this model, but for sake of argument, I would like to just continue with this model where we impose the common factor model to sigma E. Also, because in the end, we will see that if we accept this model for now, that our final tweaked model actually fits quite reasonably compared to the unconstrained model. So I will continue with this model. Well, finally, what we can do is apply the common factor model, as shown here in the circle, to our sigma A, right, to our additive genetic effects. Well, at first glance, we see, again, with the 2 degrees of freedom likelihood ratio test, it seems that the model fits well. We can accept that the common factor model applies to the additive genetic effects. But something weird is going on with the results of this model. Because if we look at the residual or the phenotype specific, so unique additive genetic effects, we see a very large negative value for the unique additive genetic effect on biceps. And this is weird, right? Because we're talking about variances. Variances can never be negative. So, well, first, this is a reminder to always check very well your output when you're doing these kinds of analysis. Second thing, this is what I see or what we see in general a lot when you work with multivariate data. So in this case, the negative residual variance is called a Haywood case, and this is often an indication that this variance is actually very close to or actually equal to 0. So a practical solution would be to simply fix this residual variance to 0, or simply drop it from the model. So let's do that. So this is what is shown here in this box, right? I apply the common factor model to sigma A, and on top of that, I fix the first diagonal element in the residual matrix to 0. And then when I compare this with model 4.4, so then we have a 3 degrees of freedom difference, we see that the model still fits compared to this model. So it seems that there is a common additive factor influencing all the phenotypes, and that there's no unique additive genetic effect on biceps. We finally can do, as I said earlier, is compare this final model 4.5b, sorry, with model 4.1, so the fully unconstrained ADE model, and we see that the model fits reasonably well. So if you would test this model with a significance threshold of 0.05, you would reject the model, but then again, we did quite a lot of different tests, so we should probably take a more stringent significance threshold, right? So in that sense, a threshold of 0.01 or 0.001. So in that sense, we might accept the model. Of course, in reality, by the way, you should never do this. You should, of course, determine your p-value threshold before model fitting, but this is just for didactic purposes. Let's accept this model and continue with it in the next slides. So after all this model fitting, it can become quite a bit confusing. Like, what does the final model look like? Well, this is actually it. This is our independent pathway model with a tweak, or a final most optimal model, showing that there are common additive, non-additive, and non-shared environmental effects to all phenotypes on the top right. There are no unique dominance effects. Biceps is only influenced by a unique non-shared environmental effects, while the three other phenotypes are also influenced by additive and non-shared, additive genetic and non-shared environmental unique effects. So yeah, this is all fun and games, fitting all these models, but you might wonder why, okay, what can we do with it, or what does it tell us? Well, in the next slides, I hopefully will show you that independent pathway model can give us very valuable insights about the genetic and environmental architecture behind different phenotypes. So again, just to show you the model, we can of course also show the unstandardized results, which I have done here. And we can use these results to answer questions about specific concrete questions about the variance decomposition of triceps, for example. But with these unstandardized values, it's a bit, they are a bit hard to, or difficult to interpret. So, but of course we can standardize them, these values, by simply dividing it by the total variance of each of the phenotypes, which I will do on this slide for triceps phenotype. So let's start with the additive genetic effects in red. So to get to the common genetic effects, we simply square the factor loading. This is the common additive effects. And then we add, to get to the total additive effects, we add the residual unique additive genetic variance. Well, keep in mind that we do not need to square this unique additive genetic effects, right? Because it's already, we simply estimate the variance. It's already a variance. This is a factor loading, so to get to variance, we need to square it. Well, for the dominance genetic effects, we only had common effects, so we simply square the factor loading. For non-shared environmental effects, we have, again, common and unique non-shared environmental effects. To find the common effect, we square the factor loading, and we simply add the unique non-shared environmental effect of 0.53 to get to the total non-shared environmental effect. And if we add this up horizontally, we get the total variance of the triceps phenotype. So then to standardize it, we simply divide each part by the total variance, right? And then we have the standardized additive, non-additive, and non-shared environmental effects, both common and unique, on the tricep phenotype. This immediately shows you that the majority of the variance in triceps is due to dominance genetic effects, and that these are all common to all phenotypes. So we can also show these values in our path diagram. So this is the standardized, these are the standardized results for our final optimal independent pathway model. So what we can also do is nicely show it in a table. This is maybe what you would like to do in a paper when you write a paper on these kinds of analysis. So these are exactly the same values in the previous slide, but then in a table to give you a nice overview. And what we can do based on these values is calculate the narrow sense and broad sense heritability based on this independent pathway model, on our optimal model. So to get to the narrow sense heritability, we simply have to look at the additive genetic variance, but we are looking at the total additive genetic variance. So we add up the common and unique additive genetic effects. So this column here is the narrow sense heritability, the total effect of A. Well, to get to the broad sense heritability, we simply add up the total A effect by the total D effect, and of course the total D, remember this is only due to the common factor. So these are the broad sense heritabilities. You can also, I also shown it in a nice graph. The narrow sense heritability you can find looking at the red parts, light and dark, common and unique. To find the broad sense heritability, we look at the red part plus the green part. So we see that they are roughly the same. So another way of expressing or communicating your results is to express the common and unique effects in percentages for each of the variance components separately. So here, for example, I've done this first for the additive genetic effects. Well, we fixed the unique additive genetic effects on biceps to 0, remember? So here, of course, the additive genetic effects are fully for 100% due to the common factor. For triceps, if we divide 0.158 by 0.253, if we divide this, then we get that, see that 62% of the additive genetic variance is due to the common factor and 38% due to its unique factor. Well, we see that, of course, for B, 100% is due to the common factor. And for E, we see that the non-shared environmental effects are mostly due to common effects, and this doesn't differ that much between phenotypes. So one conclusion, like when you're writing a paper on these kinds of model, one conclusion for this particular model could be, well, you could say the additive genetic effects vary considerably across traits, but this is not the case for the D effects, and also less so the case for the non-shared environmental effects, right? Because these are roughly the same cross phenotypes. And actually, what we see when we look at the additive genetic effects, then we see that for the subsc and supre phenotypes, these effects, additive genetic effects, are mostly due to their unique phenotype-specific factors, right? So we actually see two blocks of variables, kind of, namely biceps and triceps, where the majority or all of the additive variance is due to the common factor. And we see the other two phenotypes where most of the variance is due to the unique factors. So this could maybe lead to the hypothesis that this is due to the place on the body, right? The biceps and triceps are very close to each other. So maybe this is an explanation for this finding. So hopefully this shows you that this is really the merit of the independent pathway model. We would not be able to come up with such hypotheses or draw such conclusions based on the unconstrained ADE model, because then we don't distinguish between common and unique effects. So one thing I have to add here, by the way, is that, of course, these percentages only express the relative distribution, right? So here for this variable, subsc, 29% and 71%, this is in relative terms, but of course in absolute terms, the contribution of additive genetic effects is very small. You have to keep this in mind when presenting the results. So here on the left, again, it's just the same as I showed on the previous slide, but now again, as a fancy figure, right? For the additive genetic variance, biceps, all the variance was due to the common genetic effect in green, so 100%. But for the other three phenotypes, it was more mixed. Again, keep in mind that this is only in relative terms. So what you might want to do is pose this this figure on the right next to it, because then you can say, okay, biceps is fully, the additive genetic variance in biceps is fully due to the common factor, but then the contribution of the additive genetic variance to the total variance in the phenotype is only 25%, right? So, and one final way of expressing the results, presenting the results of the independent pathway model, and this is my final slide, is to express the correlations in terms of the parameters of this model, right? Because if we think back to all the way to the beginning of this lecture series on multivariate modeling, what is unique to multivariate twin modeling, or why do we do this in the first place, is because we want to say something about the variance decomposition of covariances or correlations between traits. So we can, of course, do this using the unconstrained ADE model, simply estimating these variance components, but we can also derive them from the results of our estimated independent pathway model. As I mentioned earlier on the slide, if we want to find a correlation between two items or traits, we can simply take the factor loading of the one trait and multiply it by the factor loading of the other trait. But now, of course, we have three factors. So what we can do is calculate the contribution of A, D, and E to the correlation between, for example, biceps and triceps. So let's do this for the correlation between biceps and triceps, which was around 0.89. In terms of the present model, well, first for the additive genetic effects, let's start with the contribution to this correlation by E. So because these standardized values were based on variances, so squared values, we first need to take the square root. And if we do this, then we see that the contribution of additive genetic effects to the correlation between biceps and triceps is around 23%. The contribution of D, so dominant genetic effects to this correlation, is about 60%. And the contribution of non-shared environmental effects to this correlation is about 17%. So now, one thing to note is that these unique additive and non-shared environmental effects do not take part in these calculations. And this is because earlier I said, well, these unique genetic and non-shared environmental effects is actually what makes these phenotypes more different from each other, right? They only contribute to their variances and not to their covariances. So that's why if we want to calculate the contributions to the correlations, we only look at the things the phenotypes have in common. So this concludes my talk on the independent pathway model. And in the final video, Connor will talk about the common pathway model, which is a psychometric application of the common factor model within the twin model. And Connor will tell you all about what this means.